Hey class. So I want to move on now and talk about the transformation pipeline. So we've learned about transformations and how you can take a point from one coordinate system to another using rotation, translation, scale, that kind of thing. There are other ways to do it too, but that's the basics of what you use. Now, you end up with like this transformation matrix that you use to make that coordinate change. However, usually for reasons to help simplify the problem, although at first it might seem to have the opposite effect. We have multiple transformations that we build, multiple matrices that we build. So I want to introduce you to the transformation pipeline. So we can go all the way from object, so our object space, to our raster space, okay? So this is our transformation pipeline. So let me see if I can get this to work. So here's our, what colors am I using? Here's our object space, and I'm going to draw this nice little object for us. I have an object like that, okay? And this is what we call object coordinates, and we just learned about that in the previous section, where centered on 0, we don't worry about the rest of the world, and we just draw it, usually scale -1 to 1. Doesn't really matter as long as we do some standard and we know what we're doing. Now we need to transform that using some kind of matrix to the world coordinates. Okay. Now the world coordinates are often in 3D, not necessarily, but we'll just do 3D for completeness. They could be 2D. You want to transform it into world coordinates. So somewhere in the world, I'm going to draw that object, rotated and scaled and placed right over there. Now keeping in mind, that object still has its own local coordinate system, right? It's still centered on its own, like it was created in that coordinate system, but now we've moved it into the space using our transforms. And we use that, we do that using the matrix called the model matrix. It's just called the model because that's our model, right? Like a model airplane. Not a business model, model airplane. So we move from object coordinates to world coordinates using that model matrix. Now I'm going to see if I can leave myself some room. I can tidy this up after, because I want to make some notes on here. Model matrix. In fact, why don't I do it this way? I have a different idea. I'm going to try something new. If it explodes and doesn't work, I apologize. So here's the model matrix. The goal of the model matrix, that's the one we just talked about, is to transform from the object coordinates to the world coordinates. Okay, so object coordinates to the world coordinates. And remember that the world coordinates too, we just make that up. We come up with our own scale. One is a meter, one is it doesn't really matter, but we have the standard world coordinate system we've come up with. We use this to set up our model in the world. We rotate it, we place it, we scale it. Come on. I really got to turn that off. Set up your model in the world. Okay. And because of that, you don't have one model matrix for your whole system. Typically, each model will have its own one, right? Because each model will be drawn with a different scale, different location in the world. So each model has a different matrix. And even you can have multiple matrices per object. For example, if different things move differently, so multiple per object. Yeah, different things moving differently wasn't very descriptive, was it? So you could imagine drawing a guy and then use one model for the main body, and we'll get back into this, but then as the arm moves, it's a different model, and you can position things within the body, okay? So you'll have multiple model views model matrices per object. And most of the work you're going to do in building your world goes here. This is where you spend most of your time. Okay, most of your work goes here. Cool. So we have this model matrix that we use to convert from object coordinates to world coordinates so we can place our things in the world. Now, we have another coordinate system that I want to talk about. The next one you might not have really considered too much before. But one thing that we like to do in 3D and even in 2D is we put things in the world, but we also want to change how we're looking at it without redoing everything. So we put an eye in the world, or a camera, and you'll often see a camera drawn like this. Eyes are often also drawn like this. That's an eye in 3D because it looks this way, eyelashes. But we'll put a camera in the world, and we say, look, the camera's, here's the up direction, it's pointing this way, and here's what it's looking at, okay? So you put a camera into the world, so we need to transform our coordinates from the world coordinates to what the camera is seeing. So the camera here might be looking at the object. So here's the world axis. I'm going to draw that in a different color. Here's the world axis, right? And it's looking at our object zoomed in like that. Now it still has its own local coordinate system. Here's the world coordinate system, but now we've introduced a brand new coordinate system for our camera. Getting messy here, right? We have a new coordinate system for our camera. These are called view coordinates or camera coordinates. And this is really nice because we set up our world. I don't care where you are in it. I don't care where you're looking at it. We just set up the world with everything in a nice coordinate system. And then if you put a character in the world, or if you want to follow something, even in 2D, you can place the camera somewhere and look at the world differently without having to rethink up everything else. All you need to do is create this transition right here from the world coordinates to the view coordinates, and we do that using what's called the view matrix. I'm going to highlight these because this is getting kind of busy. So we do that using what's called the view matrix. The view matrix converts from world coordinates to my camera. So view matrix. So the view matrix transform from the world coordinates to our view, our camera, okay? And this is really useful. We use it to move a camera or a view around without worrying about the objects. Objects locations and things like that, right? Because if I've drawn my object in its own local coordinate system and I've drawn them with model matrices to place them in the world, that's set. Now if I want to have a different view on it, I just change the view matrix. And you might think I'm moving a camera around the world, but what you're actually doing is you're making a basis for the camera, and we'll come back to that. And you're shifting everything in the world such that it's always right at your camera. So my camera, once I do that, in my camera coordinate system, this is my x-axis, this is my y-axis, Z goes in or out of the screen depending if it's right-handed or left-handed. And all of my points are now in camera space. I don't worry about world and sort order. It's messy. All I worry about now is in my camera space. It's left side of the screen, right side of the screen. And my transformations, it takes care of all of that. All right. So here's the magic I was going to try to do live to make more room. It worked okay. Right. So now I have an object. I can place it in the world using a model matrix. Now I can get a view on the world by shifting the world around to match my camera using a view matrix. Okay. Now let's learn about the next step. The next step is I need to, hold on, let me just draw this line. I need to convert from this camera coordinates to my screen coordinates. Okay, this is my screen. Now, screen coordinates is what it's called, but it's not raster coordinates, and we'll come back to that in just a moment. This is often called normalized device coordinates, and there's not much room there, but I'll spell that out below for you in a second. Now, the idea is, in my camera coordinates, I'm still in 3D space, okay? I'm still in 3D space. I'm still have weird scales. We now are starting to move toward the raster. So the screen coordinates, I'm still going to see my object in here. But now my coordinates are going to go from -1 to 1 on the x-axis, and then 1 at the top and -1 on the bottom for the y-axis. These are my normalized device coordinates. And we do that using the projection matrix. And the projection matrix is probably the most complicated part of this pipeline, that it'll be the most tricky to understand, especially once we get to 3D. But its job is to convert from these made-up 3D coordinates that we've come up with, or 2D coordinates, to some physical, toward a standardized raster. But we're not quite there yet. And I'm going to put a big asterisk here, which I'll come back to in a second. But let's talk about this projection matrix first. Let's see if I can... Yeah, this OneNote. I should never have used OneNote. I should have known better. Okay. Projection matrix. Okay. Oops. Yeah. This is important. I want to say it the way I've planned. There we go. Good. Yeah, what happens is in Outlook, when I scroll, it sometimes won't update. And I have to like randomly scroll to get it to update for me. So the projection matrix, it handles the transition from your virtual space, which might be in 3D or not, to the screen 2D flat space. We've seen this already in our assignment. The ortho command that I ran sets up the projection matrix, and it lets you have -320 to +320. That's kind of where we set up our world coordinates. That's where you tell the computer, this is the space I'm going to be plotting in, and you'll see now very soon how that works. So the projection matrix job is to transform from view coordinates, remember that's our camera, to our screen coordinates, which is not the raster, okay? I didn't name it, I apologize. More commonly, or unfortunately not more commonly, but commonly you will see it called normalized device coordinates. NDC, okay? And so what's really cool about that is I have this new coordinate system which goes from -1 to 1, -1 and 1. This is standardized across machines, across devices. This is set. I mean, we've agreed on this standard. Everything collapses down to this normalized device coordinates. Now you might be thinking, why would I do that? Why not go straight to the raster? It turns out, come back to that red asterisk, remember I put it up here? Let's come back to it. It turns out that extra stuff happens here that we'll come back to when we get to 3D. And having our stuff in normalized device coordinates really helps the graphics card or your graphics engine to optimize a lot of the calculations that have that happen. So we go to this normalized device coordinates, we do a bunch of extra stuff before moving on to the raster. So that's the projection matrix does that. It brings everything into this normalized device coordinates, okay? So typically, you set it up and leave it. You're not playing with it, okay? If I go back, on model matrix, we're always playing with it. We're positioning things, we're resizing, we're translating, blah, 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 blah. The view matrix, yeah, you're moving the camera around, you're having a different view, you're always playing with that. The projection, you get that working, you don't typically play with it. You maybe for certain effects, so if you want to change the field of view, or maybe underwater versus up, you can imagine different kinds of projections, but you generally set that and walk away. Okay, there's one more piece to this puzzle, which actually is not covered by a lot of graphics textbooks, which I don't know why. There's one more transformation, and this is coming back to, I'm in Windows now, or whatever you want to do, you know, some cool symbols in your menu. I want to come back to my viewport that we've talked about earlier in the course with a physical raster. Okay, so these are my viewport coordinates. This is my raster. Another asterisk, probably. Right? You can't be guaranteed anything anymore. Windows 10, for example, will now, in many cases, your viewport goes to a virtual raster, so it can do DPI corrections between your different monitors, right? So probably, but it's the closest that you're going to get to the raster without doing actual raster-specific commands, which is OpenGL version specific, and we're beyond the scope of this course. But you can, you know, basically we're going, we're going down to as far as you think are the window raster coordinates, and this is called the viewport transform. You know, one thing I want to highlight here, which actually wasn't in my notes, is this is a square space 1 by 1, but your aspect ratio might be 16 by 9 or 4 to 3. That's okay, because your viewport transformation corrects and brings it back to your aspect ratio. Okay. So if you were thinking, -1 to 1, what if my screen's a different ratio? That's okay. It'll be squished in normalized device coordinates. When we come back to the viewport, we'll stretch it out again, so it's okay. Projection matrix, viewport transform. So the viewport transform, it converts from the standardized normalized device coordinates towards the raster coordinates. These are often called the device coordinates. Okay. You might not have access to this depending on your toolkit, so you might not even be able to get to touch it. But in some systems, you get access to commands through GL viewport. So when you call the GL viewport command, you're setting up that last transform. It might also do other things like setting up your window and that kind of thing. But it's typical or often set up by your toolkit. So now I'd like to just emphasize why we're doing this course in processing. If you were doing it in OpenGL, to get your things to work, I would have had to set up these matrices for you, give you a code that creates a window, connects event handlers, does all of this stuff for you in raw OpenGL, whereas processing just does it under the hood. We've had some quirks where it's a bit slow for points, and there's a few quirks coming too, but it does all the viewport stuff, all the interaction stuff, all the event stuff for free, and you can focus on the graphics. So I think it's really cool. So these are our transforms. We take our point, we draw our thing in object coordinates, we transform into the world, we position it into the world with one matrix, then we use another matrix to bring it into the camera space using a basis, and then we project it to bring it into screen coordinates, and then we transform it into our viewport. So your points go through a lot of spaces to get from this virtual space that we've been talking about all the way to your viewport. Now I can reiterate something I said really early in the course. We don't really care about these virtual coordinate systems. You're going to get really familiar with them, and as you're seeing, that's exactly what's happening here. All right, so let's just spell this out. I have a point. So this is my point in object space, right? I'm drawing an object. I multiply it by the model matrix to bring it into world space. Then I multiply it by the view matrix to go to the view space, and then I go multiply by my projection matrix to project it into my screen coordinates. So now I have a point in normalized device coordinates. We do a lot of work there, like I said, we'll come back to that. And then I take my point in normalized device coordinates, I multiply it by the viewport matrix, and I have my point on the raster, or with a probably there. So this is all the the life cycle. It's not quite a cycle, but this is the pipeline of what your point goes through to go from your random, not random, arbitrary is what I'm looking for, object space, through to the world, a camera view, and then onto the raster. And we're going to get a lot of practice with that. Okay. I do want to mention that this breakdown, this is not like intrinsic to the math, okay? It's just convenient. It's not necessary. It's a common convenience. So it's a convenience because I can play with my model in model space and forget about it. I can place it in the world without worrying about modifying the model space or worrying about the camera. Once the world's set up, I can play with the camera without worrying about the object space. And then the final projection onto the raster happens separately. It's divide and conquer. It breaks everything down. I will say, though, that there are differences. For example, the model and the view are often combined. Into a model view. There are reasons for that I'm not sure I agree with, but I'm not really going to get into them. But that's a common thing. There's a model view matrix, and what that is are these two multiplied together, and you build them together instead of doing it separately. But that's the kind of variation that you will see. All right, I do have a slide. I'm not sure it's that helpful, so we'll. Since we've already gone through it. But here's an example of what that looks like, right? We have this point here. If I look at an object space, it's this U, this V. We translate it by positioning this arrow into the world, and you can see it got rotated and scaled or something. But in the world space, this same point is now on these vectors. And then my camera might be a bit zoomed out and looking at the axis from far away. In eye space or in camera space, it's different again. And they're different coordinate systems, but we transform between them using those standardized matrices. All right, let's take a break here and we'll come back and learn a bit more.